So here we have 2013 October November paper 42 question number 7. Says the partition coefficient of X between ethoxyethane and water is 40.0. A solution contains 4 grams of X dissolved in 0.5 decimeter cube of water. Calculate the mass of X that can be extracted from this aqueous solution by shaking it with 0.05 dm cube of ethoxyethane. So that's part 1. Now we know that the partition coefficient, right, that's the concentration of X in the organic layer. In this case, that would be ethoxyethane, right, divided by the concentration of X in water, right, is 40.0, right? They've given that to us. Now, the initial mass of X that we have is 4.00 grams. Okay, and then after the extraction, we want to know how much was extracted into the ethoxyethane, right? So let's say that the mass of X in the organic layer is X grams. And that would mean that the mass of X left in the aqueous layer is 4 minus X grams. The volume of ethoxyethane that we're using here is 0.05 decimeter cube. And the volume of water, right, the aqueous solution is 0.5 decimeter cube. Here we can just use grams per decimeter cube for our units of concentration, right? It doesn't matter as long as they're the same. So we can say that our KPC, that's 40.0, is equal to the concentration in the organic layer, that's X divided by 0.05, divided by the concentration in the aqueous layer, that's 4 minus X divided by 0.5, right? And what we get is we get 40 times 4 minus X over 0.5 is equal to X divided by 0.05. And if we solve for X here, we get X is equal to 3.20 grams. So that is the mass. That is the mass that was extracted into the ethoxyethane, right? That's X grams. The next part says calculate the mass of X that can be extracted from this aqueous solution by shaking it with 2 successive portions of 0.025 dm cube of ethoxyethane. Now again, what we're going to do here is, again, initially we just have 4 grams of X dissolved in 0.5 decimeter cube of water, right? So we have initially our mass of X is equal to 4.00 grams, right? But we're going to do 2 successive extractions, right? First, we're going to extract a certain amount of X into 0.025 dm cube of ethoxyethane. Some will be left over in the aqueous solution, and then we're going to use another 0.025 decimeter cube of ethoxyethane to extract more of X from that aqueous layer, okay? And then at the end, the total amount extracted will be the amount that we extracted in each of those steps, our first extraction and the second extraction. If you look at the first extraction, right, for our first extraction we know that our mass of X is simply 4 grams, right? And after the extraction, we don't know how much we've extracted into the organic layer. So let's say that we've extracted X grams again using 0.025 decimeter cube of ethoxyethane. And that means that we have 4 minus X grams remaining in the aqueous layer, right? And the aqueous layer has a volume of 0.5 decimeter cube. The partition coefficient is the ratio of the concentration in the organic layer to the concentration in the aqueous layer, right? So we can say over here that a partition coefficient, that's 40, is equal to the concentration in the organic layer, that's X divided by 0.025 in grams per decimeter cube, divided by the concentration in the aqueous layer, that's 4 minus X divided by 0.5. So here if you rearrange this expression, you get 40 times 4 minus X divided by 0.5 is equal to X divided by 0.025, and that gives us X as 2.667 grams. So this is how much we extract in our first extraction. So that means that we have, from the 4 grams, we've extracted 2.667 grams, right? So for our second extraction, right, we know that in the aqueous layer, okay, again, what we're going to do is we have a certain amount left in the aqueous layer, that's 4 minus X grams, right? So we know that the amount left in the aqueous layer now, is 1.333 grams, right? That's 4 minus 2.667. And now we're going to use another 0.025 dm³ of ethoxyethane to extract as much of X as we can from this remaining 1.333 grams. So now for the second extraction, we can say that the mass of X extracted into the organic layer is Y grams. And let's say that the mass of X left over in the aqueous layer in the second extraction will be 1.333 minus Y grams. The volume of the organic layer is 0.025 decimeter cube. The volume for the aqueous layer is 0.5 decimeter. Again, the partition coefficient here is 40, right? That's just the ratio of the concentration. That's the ratio of the concentration in the organic layer. That's Y divided by 0.025 divided by 1.333 minus Y divided by 0.5. So then we get 40 times 1.333 minus Y over 0.5 is equal to Y over 0.025. So here we get Y as 0.887 grams. Okay, so in the second extraction we were able to extract 0.887 grams. So we can say that the total amount extracted is X plus Y, which is 3.56 grams. Okay, so 3.56 grams is the total mass extracted, right, using two successive extractions. Okay, using two 0.025 decimeter cube portions of ethoxyethane. Now what I want you guys to do is I want you to compare the two extractions. Okay, the two methods. Right, in both methods we use the same volume of ethoxyethane. Okay, but in the first method we used 0.05 decimeter cube. In the second method we did two extractions using 0.025 decimeter cube each time. So the total volume that we used was the same. So if we did, when we did one extraction, okay, when we did a one-step extraction, right, here we used 0.05 decimeter cube of ethoxyethane. Our yield was equal to 3.2 divided by 4, right? We were able to extract 3.2 grams from a total of 4 grams times 100. So our yield was 80%. On the other hand, with the two-step extraction, right, we use the same volume of solvent, right, but we did it in two steps. So we used a total of 0.05 dm³, but we used 0.025 dm³ twice. Our percentage yield in this case was equal to 3.56 divided by 4 times 100, right? So we got a percentage yield of 89%. So we get a 9% higher yield using the two successive extractions, right? So we know that for a given volume of solvent, right, multiple smaller extractions have a higher yield, okay, give a higher yield than larger extractions, right, than fewer larger extractions.